Welcome back, students. Today in this session we are going to start with a new topic, Doppler effect. Already in the previous session we already dealt with the different topics that are associated with the wave optics, like Young's double slit experiment. We studied how interference happens, and in interference what are the criteria for constructive and destructive interference. Like this, lot of things have been already discussed in this particular chapter. So here we are going to discuss about the Doppler effect in light. Already you people might be familiar with the Doppler effect that is happening with the sound, where the things that are going to happen here are quite similar to what you have already experienced with the sound. But there we will deal with the frequency of sound. Sound is literally a longitudinal wave. Here we are going to see the similar effect with the light, where light is going to be a transverse wave. So this is the major difference between the sound and the light wave. But the things that are going to happen are going to be quite similar. So the phenomenon of apparent change in the frequency of the light due to the relative motion between the source of the light and the observer is called the Doppler effect. So due to the relative motion between the source of the light and the observer, we are going to see how the frequency of light is going to change, okay, for the observer who is observing the light, is what we are concerned about. Okay. Here, before I could go into this, I would like to make a disclaimer saying that light is not the ordinary things that we see around, because the speed of the light is the ultimate limit for the speed. Okay, it is called as cosmic speed limit, which means no other object in the universe or nothing else that you see in your universe can exceed the speed of light. So whatever that we are going to discuss in this particular topic is completely based on the non-relativistic aspect. Non-relativistic aspect in the sense, the objects that we are going to see will travel much slower than the speed of the light. Only then this particular phenomenons that we are going to discuss will be applicable. So now you can ask me question, sir, what happens if the source, the light source, travels close to the speed of light? In that case, the formula and the approach that we make to the frequency of light will be completely different. So for class 12 and for the NEET examination and for JEE, we constrain ourselves for the non-relativistic aspect of the light. Yes. So to begin with, already in the sound we would have dealt with different factors, like the source of the sound moving towards the observer moving towards the source, where source and observer both move in the same direction, both move in the opposite direction. So we have discussed many scenarios over there, but here it is going to be pretty straightforward, where the source of the light moves towards the stationary observer. Okay, the source of the light is going to move towards the stationary observer. For example, you are standing on a road, whereas a motorcycle that is flashing its headlight is approaching you. The scenario is something similar to that. So in this case, what I am going to show you is how the frequency of the light observed by the observer who is at rest is going to be. You see, mu prime stands for the apparent frequency, which means the frequency of the light observed by the observer, and V stands for the velocity of the source with respect to observer. Okay, it is with respect to observer, not with respect to ground. Okay, and of course C stands for the speed of the light. Okay, now mu prime is equal to mu into 1 plus V by C. Mu into 1 plus V by C it is, where V stands for the velocity of the observer, sorry, the velocity of the source with respect to the observer. So here you can see that the velocity of the source is not going to exceed the speed of light. So in no case this ratio can be greater than 1. That's a very important aspect, make a note. So in no case this ratio will be greater than 1, and mu prime is the frequency of the light absorbed by the observer standing in front of the moving source, and coming down, that expresses the apparent wavelength. So, the wavelength is nothing but the inverse of frequency. So, that is mu prime. Inverse of mu prime is lambda prime, and inverse of mu is lambda. The only difference is you will just get a negative sign over here. So, that is the only difference. Likewise, now coming to this side, where the source of light moves away from the stationary observer. Okay, where you being an observer, again you are standing on a road and the light is going away from you, like a vehicle which is flashing a light is moving away from you. So, here in this case the variables are the same. Mu prime stands for the frequency observed by the observer, and mu is the original frequency of the light from the source, and v stands for the velocity of the source itself. So, this apparent frequency is nothing but mu prime is equal to mu into 1 minus v by c it is. Similarly, if we try to calculate the apparent wavelength is nothing but the inverse of the frequency. So, mu prime is written as lambda prime, mu is written as lambda, and 1 here you have negative. So, you will get positive in terms of apparent wavelength. So, that is the only difference that you will find in these two successive cases. So, now we move to the third one, which is very important case. Listen very carefully. So, in this case, when the source of light is moving towards the observer, what really happens is your frequency increases, your apparent frequency increases, so your apparent wavelength decreases. So, that is the reason why your apparent wavelength is actually less than the actual wavelength. So, if your wavelength is actually less than the original wavelength, then what happens is the spectrum actually moves towards the red colored one. You see, the spectrum of radiation from the source of light shifts towards the red color. Okay, it actually shifts towards the red color. Okay, you might not be aware of what is happening here. I will let you know soon. Please wait. So, this is called as the red shift. This is called as the red shift. Similarly, on the other way around, here your apparent frequency, when the source of light is moving away from the observer, the apparent wavelength will be higher than the actual wavelength. So, the spectrum of radiation of the source of light will actually shift towards the violet end. It shifts towards the violet spectrum end, where it has a different wavelength. So, if you see, there is a huge variation of wavelength from your red to violet. Okay. So, because of this change in the motion of the relative motion of the source from the observer, there is going to be a huge amount of shift that is happening. Okay. So, here you see the red light is the one which has got a greater wavelength. So, that we already have studied in our lower classes that red color is used in the signals in order that it is all visible from a very far distance, because being the it has got the higher wavelength. So, it travels a huge distance. Okay, it travels a huge distance. So, that is what I am trying to say. Likewise, in here on the other case, your violet color has got the least wavelength, so it does not travel a long distance. That is the reason why it is called as the red shift and violet shift. But this might not be so visible for you in the practical cases, but this Doppler shifts are so prominently visible during the night time with the stars. Okay. So, you know that stars have their own light. So, light comes from star to earth from a very long distance, and you also know that universe is expanding rapidly. So, few celestial bodies that you see around the universe in the night sky seems to move away from you, or you move away from it, or sometimes you move towards it. So, we actually observe the spectrum from the star and see how it really works using the Doppler effect. Okay, depending on this shift, I will take our Earth to be a stationary observer, and I will take my star to be a source of the light, and I will see which color I get. If it is going to be red color, I can say that the star is moving towards me. If it is moving away from me, then I can say that it is a blue shift. In fact, violet is not prominently seen, it is called as blue shift in the case of stars. So, these are the two important things that you should know as far as the Doppler effect is concerned. There were very few questions that were rarely asked from the Doppler effect, but still you have to learn it. Maybe you might get a theoretical question completely based on this. So, with this note, we come to the end of this session. We will again meet in the next session with a different set of topic. Thank you.